To all the teachers and students of the Indian Academy. It's actually 3 p.m. for me, so it's also kind of evening for me. And I am really grateful for this invitation. I feel it as a as my pleasure to share some exciting information that I have learned while a PhD student in astronomy. And thanks a lot to the organizers, especially my dear friend Shindo. So thanks a lot, and I really look forward to discussing with all the students who have joined this, and I appreciate this effort to organize such events, which would increase the scientific temper of the youth, and that is really important in the current society. So before starting, I would like to inform that no, I consider this as more or like of a interactive session. So it's better that no, if I ask something, I don't know if you will be able to talk, or at least you can type in the chat. So if I am asking something.
They are able to unmute themselves.
Sir, we
Ah,
can talk.
okay, cool, cool. So let's see how it goes. So today, the topic is very attractive. I guess the unraveling the mysteries of dark matter. So will us really unravel the mysteries or not? We will see at the end of the talk. But to start with, so Shindo has already given an introduction about me, and I would like to say that I am currently in Poland, and in Poland, the city of Krakow. So a few pictures from Krakow mm, to show you, it might be interesting for those who like seeing beautiful cities. And then within inside the city of Krakow, I do my PhD in the astronomical observatory of the Jagiellonian University. So this university is one of the oldest in Europe. It started around 1300s, and this is the observatory where I do my research. I'm currently sitting in this building, this building. Okay. So, and these are a few pictures of the facilities that we have in the observatory. We have a few telescopes, and we, when the weather is good, we use these telescopes to observe the some objects like moon. Here you can see the picture of moon that we took during one of those sessions. And yeah, so we to begin with, I'm first planning to take you through a small journey, a zoom out journey from our Earth. So we all know that we live in this beautiful blue planet called Earth, and Earth is a part of the solar system where Sun is at the center, and we have other planets which revolve around the Sun. Also, our sun has some friends who are nearby them. So this is the immediate neighborhood of sun. I mean, because my entire point is no, sun is not alone in its neighborhood. It has its neighbors also with it, and then we are the solar system is in a galaxy. Uh, can someone tell the name of the galaxy in which the solar system is?
Milky Way
Milky
galaxy.
The
Way.
Milky
Ah,
Way.
yes, yes,
Milky Way.
exactly. Exactly,
The Milky
exactly.
Way.
So Milky Way is the galaxy in which we are. So this is just the image of the Milky Way, which is created in a computer. Because actually you cannot take the photo of Milky Way like this, because for that you have to go really far away and outside the Milky Way to take the photo. So since that is practically impossible, we create these images in the computer. So, and this is the center of the Milky Way, and we are somewhere here. Solar system is somewhere here. Yeah, so this is basically the distance that we are far away from the galactic center. And I'll just show you how the galaxy or our Milky Way looks for us from the Earth. As I said, this image which I have shown you before, it is from outside the Milky Way, but how does it look? Because we are sitting inside the Milky Way, we are sitting in this one arm, and then how does the entire Milky Way look for us? So I'll show a video. So this is a video of how the Milky Way looks. So I hope it's clear for you. Maybe there might be some mm, delay. So this is what you see as Milky Way, the white patch, because we are seeing it from one side, so we can only see as a patch on the sky. And really, we cannot see it in our daily life. The problem is that we all live in we all, most of us live in cities, and the light conditions in our place is like, it's not favorable for us to see Milky Way. You really need to have a very dark night without much light on the ground to see the Milky Way clearly. So that's why we have these telescopes installed far away from the city. We have in deserts or in very isolated regions or on mountains. So this is one such collection of telescopes which observe the Milky Way. So they take the images of the Milky Way by continuously looking at it, and then so we get to know how our Milky Way is like. So that is how we get more information regarding the shape and other things regarding the Milky Way. So to Milky Way is a galaxy. So galaxy is a combination of stars. It has other things like dust, gas, and many other things. We will get to know about them later. Yeah, so this is just one other picture of the Milky Way, which was taken at the Paranar Observatory in Chile. So Chile is one country which has quite isolated regions, deserts, which are quite good for our observations. So for that, many telescopes are there in Chile. So now moving uh, outward, like we are zooming out, can see that our Milky Way has an immediate neighbor. Can anyone guess the name of the galaxy which is near to
Andromeda.
Andromeda? Yes, exactly. Very good. So Andromeda galaxy you can see here. So this is a Milky Way, and then this is the Andromeda galaxy. And then associated with it, we have many other dwarf galaxies, which are like small galaxies and all. And all these things form a group of galaxies. So as I said, stars combine to form. Sun is a star, so stars similar to Sun combine to form a galaxy. Then galaxies of similarly they combine to form group or something called galaxy clusters. So these clusters, keep this word in mind because we will come back to these clusters later. Yeah, so then zooming ahead, we can see that these clusters, they also combine together to form superclusters. So this is how our universe will look if you look a bit from the outside. That these are the galaxies. All these white things you see here, they are galaxies, and then the galaxies kind of connect to each other, and they are connected in this way. And now what do we do if we zoom out further, like if we are seeing our universe from the entire outside, then it will look something like this. So as I told you before, that these are the images that we create in a computer, because there is something called computer simulations which let us uh, create these images and all using computer programs. And I'll just show you how our universe looks and how this universe looks. So this is one universe created by one code. So as I showed you, these white or this yellow thing points you see, they are all galaxies. They are concentrations of masses, and what you see here is a big cluster of galaxies. So this is a galaxy, then there are many galaxies over here. So you can see a huge concentration of matter, of mass in this region. And also you can see, so this is called a galaxy cluster, like, galaxies clustered together. And also there are regions where you can see, like, filament like structures. See, filament like structures, you can see where these are connected to other points. And also there are even regions where there are not many galaxies. So our entire universe, which was created in this computer, it looks like this. So you can also create one, like, if you continue if you do research in astronomy, and if you are into computer simulations, if you are really good in computer programming, then you can also, like, create your own universe. Actually, there are many competitions now where people create their own universe, and then, like, we check which universe is the real universe. So it's actually fun. Okay, so this is how the entire universe looks from the computer, from the outside point of view. And uh, let me ask you, like, I have shown you stars. I said that stars come together to form galaxies. Galaxies come together, they exist together to form galaxy clusters. What is one thing that causes all these? There is one thing that lets these galaxies, like, come together, be together. What would be that? Can you can you guess what it is? Because
Gravity.
okay, great. Yes, exactly. So gravity is one force that let all these things happen, right? Like, because everything, like a star, galaxy, everything, they have mass, right? And we know that if there is mass, then there is a force of gravity, which we all know, which can be calculated using this equation, where mass actually matters. So where there is mass, there is gravity, right? Okay, so this is gravity is one thing that causes all this, and this is just one snapshot of the universe which I have shown you before, and it is called the cosmic web because, like, it looks like a web of how spiders make webs. It looks like a web
Cosmic
structure.
web.
Okay, so gravity is one thing that causes all these things. So keep that in mind, and we believe that this is the entire universe, like, because this is what we see. We see stars, we see galaxies. That's it. That's what we thought. But it was it? Let's see. Actually, once one scientist, Vera C. Rubin, so she was studying how fast is a galaxy rotating. Okay, so as you know, our Milky Way is also rotating. So there's a center for the Milky Way, and then it is rotating, and you can see. So this is one example. It's a graphical example of one rotating galaxy. So if it is rotating, we see that with every rotational motion, we know that there is a centripetal force associated with it. And this rotation of these galaxies are caused due to the gravity that is caused by the mass of the objects within the galaxy. So we can, like, equate the equations of centripetal force and the force of gravity to create a relation between the mass and the velocity of the rotation. So if you want to calculate how fast a galaxy is rotating at, for example, this point, then you just need to use this equation with the mass which is, like, enclosed in this region, right? So we can actually see the galaxies, and then using the light that we get, we can estimate the mass of different regions, and using the mass, we can predict the velocity at which these things rotate. Now, if we think, we can see that, okay, there's a huge mass concentrated here, so this region should have a fast moving, fast rotation. But as you go outside, then these regions have very less mass around. The mass profile changes, like, the density changes. So due to that reason, we estimated that this part of the galaxy should rotate slow compared to this part, as you can see. So this is the expectation from our understanding. But when Vera-C Rubin observed, this was not what we actually found. So if you see the graph here, this is the velocity and the distance from the center, and as you go far away from the center, we expect that the rotation should reduce, the speed of the rotation should reduce, but we actually observed that it is not reducing. We observed that the outside rotational velocity of the galaxy is also remained the same as inside, but we do not have enough mass that we observe. So what is the thing, for example, this is yet another picture of the same curve, that this is what we observe if we know they calculate the mass, but this is what we actually so this is what we calculate, and this is what we actually observe. So there's a huge difference between what we observe and what we predicted, right? So that means, there is a discrepancy, and these discrepancies have always created always contributed good, very, very useful scientific discoveries. So this is one such discovery which led to what we call something that I'll come to later. So now we have calculated the velocity using the mass that we see, right? Okay, we don't see the mass, but we see the stars and everything, and using the what we see, we calculate the mass. So using that, we calculate the velocity. But it seems like the velocity has some more contribution from the something that we do not see. So there are something in the galaxy which we really do not see, and and we know that it has mass, because it is it is affecting the rotation of the galaxy. So if something that has mass, it's matter, then we cannot see, so it's dark. So that is how we came to the term the dark matter. So this observation of the galaxy's rotation, it led to the proposition of having something called the dark matter, where there are still matter around this outskirts, in the outskirts of this galaxy, which we cannot see. So that is making the outskirts of the galaxy rotate faster. Now, it is not the only place where we see the evidence of dark matter. The other thing is galaxy clusters. So coming back to the galaxy clusters, which I have said before. So what is a galaxy cluster? Anyone?
Sir, a galaxy cluster is a group of galaxies.
Mm-hmm. Exactly. So galaxies, they gravitationally attract together, they come together, they form a cluster of galaxies, right? So what you see here is a cluster of galaxies, and so within this galaxy cluster there are huge mass distribution, and this mass distribution affects the motions of galaxies. So I'll show you one video where, okay, so this is a galaxy cluster, it's a computer simulated galaxy cluster, and just observe each galaxy. So these each points that you see are galaxies, and just observe how they behave in the galaxy cluster. So you can see that all the galaxies are moving, right? All the galaxies are moving. They are moving to each other. Then they sometimes they combine together, they merge. See, there are two giant galaxies merging here. You can see the merging process here. At the same time, some galaxies are being thrown away. So many things happen. So the main point is that the galaxy clusters. Yeah, so if there's a cluster, then the galaxies in the galaxy clusters are moving with the very random velocities. So we do not know how, so with the different velocities, and these velocities also depend on the mass content of the cluster. So we can compute how these velocities, how in what velocity, what direction, and in what magnitude these galaxies are moving, and then using that observation we can calculate the amount of mass which is in this cluster. So in there also, the mass that we calculated using these velocities were not agreeing with the mass that we see. So there also it shows that okay, there is something that we cannot see, and that can be dark matter. So we have one more evidence for dark matter, and we have more.
Yes, sir.
Okay. Yeah, so now other thing, like one other evidence, it's just a basic slide, like how do we see, like when there is light which is being reflected by some object, then it reaches us, then we see. And we always, our human brain always thinks that light is traveling in a straight line, right? So using this concept, we know how does a magnifying glass work, right? So if we have a lens here, a convex lens, then the object which is here, the light that is coming from that object gets bent by this lens and then reaches our eye. So but when our brain interprets it, we think that okay, this light is coming from a straight line, and then we see this the image in a magnified dimension. So here the light was bent due to the lens, right? Now similar thing happens in astronomy. For example, this one. So I'll tell you what it is. So it is not any object which is like actually like a snake. Like it appears like a snake, but it's not a real object which is like this. What happens is that imagine there is a source which are like far away from us. So it can be a galaxy or a star or something like that. And generally we get this light straight from the source and we see it, right? But in case there is some mass which is like in between us, okay, let's say there is a huge cloud, or there is another galaxy which is on the way from the other source to us. So there is mass. This mass can attract light. So it's very simplified way of me saying it, but it involves a lot of things called the general relativity principle, which is like which tells us how the light bends. So due to the mass, this light bends and then reaches us. And due to this reason, we see two different images of the same source at two different regions. So instead of seeing this source at here, due to this mass, the light bends and we see the image of this source here and here. Okay, so this is like a lensing effect. Let's say here instead of so the here in a magnifying lens, the lens bends the path of the light, but here some mass which bends the path of light. So this is called gravitational lensing, because this lensing is caused due to the gravity that is caused by this mass. Now, do we see it in real life? Yes, we do. That is what I have shown you before. So this is the image that, so this is one mass which is in front of us, and this is the image of a galaxy which is behind it, which which turned it into a curved image. Similarly, there are other things also we see, which is part of gravitational lensing. So why do I mention this gravitational lensing? Because as I told you, this amount of the bending that you see here, the amount of lensing that you see is dependent on the mass of the object which is in between us, right? So if it is more massive, then it gives a more lensing effect. Now if we have galaxy clusters here, or big galaxies in this region, we can estimate the mass of the cluster or the galaxy using this lensing observation. Now that also gives us the estimate of the mass, and we see that okay, that is that there also exists some mass which we cannot see. And that is also something called the dark matter. So what we already know about dark matter is that it's not visible, it's dark, we do not see them. Then it interacts only gravitationally, because like it attracts mass. It does not have any other interactions. That is why we cannot see them. And it actually matters because it is affecting the motion of the galaxies. Also, this dark matter is one reason why our universe still exists, and it is also one reason why we also exist, because the structure which I have shown you before, the cosmic web, it was all created because there was dark matter in the beginning of the universe, and then it led to the formation of these structures. That's all about dark matter, but the darkness in the universe, it doesn't end here. We have something more. Uh, for that, we all may know that our universe is expanding. Edwin Hubble have discovered that using observations that galaxies in the universe, they are moving far away from each other, and that means that our universe is expanding. At the same time, it is speeding up. Now, what is the reason? What is causing this universe to expand? For example, we have a balloon and we need to blow it. So we have to give some energy to blow it, right? There should be some form of energy, either we should blow it from our mouth, or we should use a other air pump to do that. And somehow there should be energy that should create this process, right? So here also we have such an energy that expands this universe, and that is called dark energy, because it's dark in the sense that we do not know much about it. It is still mysterious. So there is dark energy which is pushing out the objects. At the same time, there is dark matter which is keeping it not flying away from each other. If there's only dark energy, then we will all fly away. But there is dark matter also which keeps it intact. Now, our universe, the entire universe, is 68% dark energy, because it's majority of dark energy, and 27% dark matter, and there's only 5% that what we see as stars, as galaxies, gas, etc. Everything else is dark. So imagine how vast is our universe, and we are only seeing the 5% of it with our eyes. Yeah, we are mostly invisible. And this is just a perfect example of how we can connect it with. So this is a night sky view of mainland Europe, where you can see big cities being illuminated very highly. And then also there are regions which are dark. For example, this part appears dark. And okay, do you know which country is this? Any idea? Any guess?
Spain,
Sorry?
sorry, Spain or Greece.
No, it's not Spain, it's not Greece.
Iceland.
Oh, great. Yes, it's Iceland. So you can see Iceland is almost dark. And also there are certain regions in the Scandinavian, this is Norway, some regions here which are dark. And also this is which continent?
Europe, sir.
Europe is this one. I'm talking about the one below.
Africa.
Yes, this is the African continent. You can see some part, majority of the part is also dark. So looking from the sky, we see that okay, there are light from all these regions, uh, and there are no light from these regions. But does it mean that there is nothing there? No, actually, there are things existing, but just that we cannot see them, right? Yeah, so this is the concept of dark matter in the universe and dark energy. There are things that dark matter is there, but we cannot observe them. We cannot see them. We can observe them. Sorry, we can observe them in the sense that we can observe the effect of dark matter, but we cannot really see that dark matter exists. Now, it's a very trending field of research in astronomy and cosmology, studying about dark matter and dark energy. And as a person from the astronomy community, I welcome you all to, like, to unravel the mysteries of this dark side of the universe, not only dark matter but dark energy, to know more, because as I said, it is still mysterious. We have to study more, have more experiments to understand about the dark matter and dark energy. And what I have mentioned in this talk is about our evidences, like, do we really think that dark matter exists? Yes, we do, and these are the evidences that we have. And more to come. So researches are happening, and I hope in future we will have some exciting discoveries about what these dark matters are, like, what constitute them. Are there some particles, or are there antiparticles? There are, like, many theories for dark matter. Also, there are even theories which says that there is no dark matter, but the problem that we see is because of our wrong understanding of the gravity. They are called modified gravity theories. So, like, there are, like, uh, n number of possibilities in the market, and I encourage all of you to take up this interest and then contribute to the field of science, maybe through this. Uh, okay, I'll stop by showing one exciting picture which my friend captured here. So this is the city of Krakow. We have a mount. This is captured from there, and there is something instantaneously special in this picture. Can someone tell me what it is?
It's comet, right?
Ah, yes, you can see a comet here, and so this was the time of a comet which was visible from Krakow. At the same time, it was a time for meteor showers. So this comet you can see continuously; it stays, but meteor, like, goes in few in a fraction of seconds, it disappears. So this was a perfect capture that we got with the comet and the meteorite. Yeah, so I think I'll stop here, and I hope it gave you some information about the dark side of the universe. And feel free to ask any questions. Thank you.
We are open to questions, students.
I have a question.
Yes, please.
Um, you said that dark matter is not visible in any way, right?
Hmm.
And only is attracted to gravity, right?
Yes, exactly.
Yeah, so aren't like neutrinos also the same?
Well, neutrinos are not really. So neutrinos interact gravitationally, but it's very weak.
Oh, okay.
So yeah, there were actually propositions that, neutrinos can be one constituent particle of dark matter, but it cannot be, because neutrinos have a tiny amount of mass with it. So they
Oh, okay.
interact gravitationally, but it's very weak. So they cannot be this thing of dark matter, because dark matter interacts gravitationally only, whereas neutrinos interact gravitationally, which is in a weak way, but and also neutrinos interact using weak forces,
Oh, okay.
nuclear
So
weak force. Yeah.
so they basically have like less mass than dark matter.
Yes, exactly.
Okay. Okay.
Exactly.
Thank you. Thank you.
Thanks.
So you said that dark energy has like a gravitational force that brings the galaxies into a cluster.
Dark matter, not dark energy.
Okay, so
Yeah.
so does dark matter have some kind of like magnetic field which brings the gravitational force?
No, it doesn't have a magnetic field. It doesn't need a magnetic field to bring the gravitational force. It has mass. So if you have mass, then there is a gravitational field associated with it. So you don't need a magnetic field. So to have this attraction, gravity can also attract. So without this magnetic field, dark matter can attract masses. Am I clear?
Yes, sir.
Okay.
So are there ways like different scientists experiment on how to find dark matter, or
You mean
have like a trace, or like some sort of proof?
okay? So the three methods which I have mentioned: the galaxy rotation curve, then the velocity of galaxies in galaxy clusters, and the gravitation lensing. All these three phenomena are evidences for the existence of dark matter. This is a few of many. There are other things like the effect of dark matter in the formation of structures in the universe, like in cosmology, like we study the evolution of the universe from its birth. So after the big bang, how the universe evolved. So on the way there was dark matter. Due to the dark matter, we had this baryonic matter coming together and forming galaxies. So these are the models of evolution of the universe that we have. And there also we it requires the presence of a dark matter. At the same time, there are, like, observations like cosmic microwave background radiations, where there also we observe the evidence of dark matter, but not directly, but in this indirect ways, because we cannot see them
Okay.
directly.
Thank you, sir.
You're welcome.
So is there a way to like kind of obtain black matter? I mean dark matter. Is there a way
uh,
to obtain it?
you mean in the lab, in our daily life?
No, sir, in a lab. Like, can you
Yeah.
obtain dark matter?
That's a very, very interesting question. As of our current knowledge, no, it's not possible. Actually, we all have dark matter around us. What I mean is, like, dark matter is not only present in far away in the outskirts of galaxies. It is present everywhere, but the amount of dark matter that is near to us is very, very small. That is the reason why we do not observe the evidence, or we do not observe the effect of it. But yeah, creating dark matter in lab, it's not yet, we do not yet have the facility to do that, or the algorithm to do that.
Okay, thank you, sir.
Welcome.
Students, feel free to ask. This is an interactive session.
Yeah, it's a very interesting questions we are getting.
Sir, is there any way we can make dark matter visible?
uh, mm, Not really, because it does in dark matter. As of our current understanding, dark matter it does only interact in gravitationally. If we have to see something, it has to interact electromagnetically, like how we feel light. Light is an electromagnetic wave, and only if we get the light from it, then only we can see it, right? So, in order to get a light from something, that thing should, like, interact electromagnetically. Dark matter, as of now, as of our current understanding, dark matter doesn't interact like that way. So it's impossible to see. Uh, yeah, but maybe in future we will observe some evidence of dark matter interacting electromagnetic. So because it's an evolving science, I cannot, like, completely say. I can say, like, till now we haven't observed it with light.
So dark matter is basically nothing, but it's the color of the universe, or the universe has no color.
Mm, that's very Okay. It's not color for sure. Dark matter is not color, but if you ask about the color of the universe, it depends how we define the color. Because in cosmology, color can be defined in many ways. But dark matter is not associated to any color. It's not something called black color or anything. No, it's not. It's matter. Just it cannot see. It cannot. It doesn't. It's not visible. That's it.
So when you're out in space with a spacesuit, can you actually feel dark matter?
If you go far away from our galaxy center, yes, you can, but not in our solar system. In if you are within our solar system, then the amount of dark matter is really, really, really small. So we cannot observe any effect of dark matter. We have to go
So,
far away.
to like either even feel dark matter, we have to go out of the solar system.
Sorry, I didn't hear you properly.
So to even feel dark matter, we have to go out of the solar system.
Yeah, even more far away from the solar system, as I have shown you in the galaxy
In the
center
places
image.
where galaxies are mostly not present and to those
Uh,
places.
Not like that. So if you see here, this is our galaxy center. So this is a galaxy center, and we are here, right? So in this
Yes, sir.
region where you see matter, there is actually a lot of normal matter. Let me call it normal matter and dark matter. Normal matter is what we see, right? Okay, so here there is more concentration of normal matter. But at the same time, if you look at regions like this, okay, where you can, okay, for example, this region where you can see almost empty space, there the amount of the normal matter is less and dark matter dominates there.
Yes, sir.
This
So
is
dark matter, even though it's attracted to gravity, it is more abundant in places where there is no
empty space. Yeah,
gravity.
exactly. Where there is empty space. Yeah.
Yes, sir. Like when we even feel it, will it be like pressure on us or something like that, or again it will feel like the atmosphere we have around us.
Uh, we do not have any experimental simulation because we cannot do that. We cannot go till there yet. But I don't think there are even any simulations which have said that okay, you will feel like that. Uh, so I'm not sure if how we feel if we go near a dark matter dominated region.
And also, when can we expect ourselves to, you know the secret about dark matter?
Uh, that it's an evolving science, as I said. That because now there are many experiments which are trying to find what are these particles, and as I said, there are even counteractive theories also, like modified gravity, because uh, because our main assumption that we have dark matter was from this equation, right? Where we see that okay, F is equal to g by r square. That is the our knowledge of gravity, and it might be wrong. That is what some people say. So there are scientists who say that there is no dark matter. There is only whatever is here, but this equation that we consider is wrong. So that is called modified gravity theories. It's also trending now, but this those theories couldn't explain other observations of dark matter evidence. So and yeah, I don't know if I can just say okay, within this many years we will get to know what dark matter is. No, it's like
At
it's
least one
science.
century to know about dark matter.
I guess so, because there are more researches happening. So I guess we will get to
Yes,
know
unless
at
some
least.
aliens come and give us some help, it will take us one century.
Sorry.
Unless aliens come and give us help, it will take.
Yeah, okay. Maybe.
Thank you, sir.
So,
Thank you.
You're welcome. Interesting questions.
so does dark matter contain molecules, let alone atoms?
Uh, we don't know. We don't know what are the particles, what are this dark matter, what is inside dark matter. But we have hypotheses where they are not atoms or molecules, but they are subatomic particles. I don't know if you have heard of the elementary particles called fermions, bosons. So there are certain, like you divide atom, you find electron and proton. Then you divide, you cannot divide electron further, but you can divide proton into quark. So these are fundamental particles where you cannot divide them into further things. So the research happens in checking if there is any fundamental particle that makes up the dark matter. Yeah, so we don't know until we detect them. We cannot say whether they exist in the form of atoms or most probably not atoms, because these atoms are made of fermions and bosons, and that have electromagnetic interactions with them. So if dark matter was with, with atoms, then it should have been interacted electromagnetically. So it's not.
Okay, sir.
Are bosons like hypothetical or?
No, bosons really exist.
Oh, okay.
They're not hypothetical. Yeah.
Iron photon is a boson.
Yeah.
Oh, okay.
Anyone else? So as you can see, there are a lot of students who are genuinely interested in science. Can you enlighten them which are the career options, or if they want to pursue a career in research, what are the steps that they have to do, or how can one become a scientist?
Okay. So so if you are if talking about the PhD, then after school there are different ways to come to PhD. One very conventional way is to go to a Bachelor of Science in subject which you're interested, physics. If you have to come to astronomy, then physics, then or chemistry or whatever subject which you're interested in. Then after that you need to get a master's of science in that same subject. Then you can join for a PhD program. This is one way. So in other way, these bachelors and masters are combined as one single program, like integrated BSMS courses. That is also there. In other way, it's like we can even go for engineering courses, like BTech. Even after BTech, you can do a master's in physics or in astronomy and then join the PhD. Masters in the subject is mandatory. You need to have a master degree in the subject. If you're talking about astronomy, you need to have a master degree in either astronomy or physics or computer science. So these are the degrees can which will let you join a PhD program. So now PhD is like you are studying a lot about the problems, and then after you finish your PhD, then you can continue working, do the research as either a postdoctoral research or scientist in research institutes. Yes, so this is the way how you can do take research as your career option.
Anyone else? In that case, shall we call it a day, sir? Thank you so much for accepting our invitation and sharing your valuable time with us. It was really indeed helpful, and I I'm certain that all the students have enjoyed your session, and thank you so much for your continued support, and we look forward to have a few more sessions with you in the future, sir.
Thank you, thank you. I also look forward. I really enjoyed the questions were very interesting, and it's
Yes.
always fun to discuss science with students. Well, it's
Sir, the
actually my
topic
first
was so
time.
cool.
Sorry.
The topics were so cool.
Thank you, thank you. So yeah, it's actually it's fun talking. It's my first time I'm interacting with school students like now, so it's also kind of new for me. Thanks so much for giving me the opportunity.
Students, I'll be posting a feedback link. Feel free to suggest your genuine feedback. Yes. Thank you so much, sir.
Sir.
Thank you, guys.
Thank you. Goodbye.
Goodbye, sir.
Bye, sir.
So, bye, sir.